Okay, welcome back. We had just been looking at some examples of the application of Bayes' theorem. So what I want to do now is give you another interesting example, which is interesting because it starts pushing the limits a little bit. What if you have an assumption and we change it a little bit? The idea there in the Bayes rule-based theorem approach is that you collect data and you know what the data was. What happens if you're uncertain about the data? So let me bring up my screen. So what happens when the data is uncertain? Now, in the standard approach, when you have you go from the joint prior, you update to some joint posterior, and the way we do it is we say, look, you open it up using the product rule, and you say, now we know what the marginal distribution of x is. If we know the data exactly, we replace this by a delta function. And this other piece here, we say, well, we do not know what that is, but I can choose anything there. There is no reason to change my mind, and so I will pick the prior of theta conditional on x. So that's the general structure. So now notice how beautiful this is here. If the update from the original Q to the posterior distribution is such that if we know this with certainty, we put a delta function, then the proper update when you are not certain is that you measure some value and you have a value x prime, but that does not quite tell you what you, the measurement always gives you some result. It gives you a number, 2.3. You write it down on your piece of paper. That's the value you got, right? But having obtained the 2.3 does not quite mean that the x has a value 2.3. There is really here some distribution that may depend on the value of x, on the value of x prime, and so that you still retain uncertainty about the actual value of x, even though you obtain this value x prime quite precisely. Very good. So this is the update. We still say, well, concerning this other dependence, there is no reason to change your mind. Use the prior. And so the conclusion is that the updated posterior is going to be whatever this distribution is, like that. Notice that here we are no longer allowed to write x prime here. It's just the same old x. And here we have a probability distribution. Now, what is this probability distribution? Well, here's an example. An example could be that this probability is something that is like Gaussian. It's proportional to minus x will differ from x prime by some amount that is proportional to with a certain probability, and here you have some error for that measurement. And so if you happen to know this function here, you just plug it there with the appropriate normalizations and all of that, and that's a perfectly reasonable new estimate of what p theta is going to be. To find p theta, you just integrate over x, you marginalize x, and so you have p theta is the integral over all the x's of the joint, and what that gives you is this integral over all the x's of the function that contains the actual data x prime and the old likelihood. So here you have your result. This result is called Jeffrey's rule. I never know. Yeah, that's it. I never know if it's Jeffries or Jeffrey. Jeffrey. Uh, Jeffrey's rule. Um, of course, physicists and experimentalists of all sorts have used rules of this type because they're so obvious uh, for a long time. Um, it is interesting, however, look at this. This is very interesting because one of the things that is clear here is that this is an interesting example in which the information that allows you to make inferences about theta is not totally contained in the actual data in the observed x prime, but it is also contained in the functional form of this probability distribution that tells you how uncertain you are about x once you have observed an x prime. In other words, the information when you perform measurements is not just contained in the data, but also in these additional pieces of information that we put there to quantify the uncertainties. And includes also it's contained in that prior likelihood function. So this is interesting. Information does not only come in the form of data. Let me write it down because this is going to be a theme in the rest of the course. Does not always come in the form of data. What Jeffrey's rule has in common with Bayes' rule is that in both cases we introduce the information in the form of a constraint on the allowed posteriors. We have a family of allowed posteriors. We do not know what to pick. You say, okay, whatever it is, it has to be consistent with whatever we measure. It has to be, this constrains what the allowed form of the posteriors is going to be. The data provides you with a constraint. It will be a delta function. If you have uncertainty, you put another probability distribution. That probability distribution provides you a constraint. So this gives you a hint that perhaps a good definition of what the most general form of information might be beyond data, information can be taken to be a constraint on our beliefs. More precisely, information is a constraint on what we ought to believe if only we were ideally rational. So that's an interesting conceptualization of what information is, because it comes completely devoid of any other form of preconceptions in terms of bits or qubits or anything of the form. It just has to do with how you believe, how you're supposed to believe, at least. Very good. Notice that, yes, indeed, if this were a delta function, then you would recover the Bayes rule again, right? There is another way to think about Jeffrey's rule, which is the following. This is same thing, but with a different name. What we would like to say is that we want to study this Jeffrey's rule using what is called nuisance variables. Nuisance variables are obviously variables that are inconvenient. This is a technical term. The idea is going to be the following. We want to update. You see, I've always come back to the same logic because the logic is sort of like universal. We want to update a joint probability distribution when, let me write it like this, when we know a prior and we know a connection between x and theta. Now, it could be, and this is the case that I want to explore here, that the connection between x and theta is considerably more complicated than just a function. And this is where the nuisance variables come in. What is this? It could be that the connection between x and theta is something that is of the form qx theta. Let me see, how do I want to say this? The connection between x and theta is actually, let me write it down. Where is it here? Is through some other variables. So let me write these other variables as follows. There is the theta I want, there is x, and there is another y. And the problem here is that you have your thetas, and then you have q, x, y given theta, and what you have here is that q is not connected to theta directly. There is what is connected to theta is going to be q. I can just use the product rule again, right? qy given theta, and then qx given y given theta. This is, so far, this is exact. But let us assume that once I give you y, x is actually independent of theta. This is the interesting case where this quantity here, the quantity x, does not depend on theta. The quantity x is related to y, and y is connected to theta. So under these circumstances, the joint distribution is q theta, and then qy theta qx given y. And so now when we do the update, x theta x y, we still proceed in exactly the same way. We say, well, we have px p theta y given x. And the way we're going to handle this is we're going to say when we measure x, we are going to, this is where the update is. Let me write it like this. We measure x and we get x minus x prime. And for this piece here, we're going to use exactly what we had before, which is q theta y given x, which is equal to, so you see, principle of minimal updating. I can choose anything I want for this guy here. I'm just going to choose what I had before. So theta y given x, and I'm going to write this as q y given x, which is presumably something I know. And here I have q theta given, sorry, y given theta given y given x. But the idea is that this second piece here is not there. It's theta is independent of x. So just like I said here, if x is independent of theta, of course theta is going to be independent of y. That's what I'm writing here. So the posterior is going to be x minus x prime, and here we have qyx, q theta y, and if we want the probability of theta, which is what we want, the updated probability, we have to integrate over x and y. Integrate over x and y, and the x, and we have the integral over dy. Yes, I should actually just write it all out. dx minus x prime, integrate dy qyx q theta y, and so this gives p theta is equal to the integral over dy of qy given x prime and q theta given y. There we go. Please notice, look at this expression here. We have an integral over the likelihood function, but the actual data gives you another integration. This is of exactly the same form we had here, in which the actual data is something like this, and the x is what I've been calling y in the next slide. So it's a different way of getting exactly the same idea. Now, this is not at all uncommon to say that you want to make inferences about a quantity theta on the basis of some measurement of x, but the connection between theta and x is highly indirect. It is that x is connected to something else, and the something else is connected to theta, and so now you have to do a more sophisticated kind of analysis. I hope you appreciate that this more sophisticated kind of analysis that go under the names of Jeffrey's rule and stuff like that do not use any different kind of logic. It's exactly the same logic that we use for Bayes' rule. That's important. That's why, well, had people realized that Jeffrey was using exactly the same logic that you ought to be using for Bayesian, normal Bayesian inference, maybe his name would never have been attached to such a rule. It is only when you realize what you're properly doing when you do Bayes' rule, as opposed to Bayes' theorem, that you start realizing that it's always the same pattern of reasoning that we're following. Very good. Oh, yes. The fact that you had this additional variable that you had to introduce here, but you don't care about the y. It's just something that forces you to do extra integrals. That's what justifies the name nuisance variables. Variables you have to include because they contain important information, but you don't care about them at all. Very good. Let me do another little development here. What happens when you have multiple experiments? One of the simplest and most reasonable ways to increase the accuracy of your measurements is by repeating the measurement many times. So let us assume that we want to infer about theta on the basis of data x, which in this case is composed of many measurements. Now, we're going to make the assumption that the various measurements are independent. So basically, you do one experiment, you do the second experiment is completely independent of what the first one gave you, and if it were not, you would probably not be doing your experiment properly. If your second experiment, the result of your second experiment depends on what you got for the first one, then perhaps you forgot to recalibrate your equipment, perhaps you don't let it settle down enough, perhaps you really don't want the first measurement to influence the second one, right? So it is a matter of experimental competence to ensure that when you repeat experiments, they're going to be independent of each other. Under that circumstance, the likelihood function, the probability of the experiments, let's do it for just two, okay? Obviously, well, if there are more, it's easy to incorporate in that information. The likelihood function for your experiments is going to be just a product. It's the likelihood function for the first, likelihood function for the second. Now, it is interesting that the likelihood functions don't have to be exactly the same. Maybe in the first experiment, you are measuring the velocity of the oil drop in a millikan experiment, right? In the second experiment, also to determine the same charge of the electron. In the second experiment, maybe you are doing a scattering of electrons, or shoot electrons at the nucleus and see where they come out. So the experiments need not be the same. However, they are independent. Under those circumstances, then, the full information about the whole thing of the prior is going to be of the form there is a q theta, and then there is the likelihoods. And if you want to include more experiments, pile them up. So under those circumstances, we can ask, we start with q theta prior, and we perform an experiment and we update. So we can say we can update by performing just one experiment, P of theta x1. This is after the first experiment is going to be given by let me just go directly for the updated P. After you collect x1, then this is going to be something like this. Prior x1 prime, that's the value you collected, and then maybe you have qx1 prime. So this is one possibility. Another possibility is that this is collect x1 first. Another possibility is collect x2 first. And so under those circumstances, what you have is now you see where I'm going with this. And so what if you collect x1 first and then you update to collect x2, or the other way around? Does the order matter? What happens if you update simultaneously, right? The question here is you collect x1 first, collect x2. Well, let me put it second then. Second. I'm changing this slightly, right? And so now we process it again. And so when you collect x1 first and x2 second, we're going to use, look at what I'm doing here. What is the prior when you're just trying to process when you're trying to, you collected first, you updated. So now the prior here is going to be theta 1. And, well, that's it. You update again. So now what is the total updating? Is going to be, you started with q theta, updated with qx1 theta, and then you update with qx2 theta, and then you have these terms here, which are qx1 prime, qx2 prime. Now, what's sort of interesting about this is that if you collect x1 first, you go from q theta to p1, then you collect x2 second, you go from p1 to p12. But the expression we get down here is exactly the same if we had done it in the other order, if we had collected first x2 and then x1. And in fact, it's also the same if you had collected x1 and x2 simultaneously, because this actually happens to be, this piece here happens to be exactly the likelihood function for the joint probability distribution. So, conclusion. When the measurements are independent, the order of updates with Bayes' rule do not matter. This is actually very important and extremely convenient. You can just keep bringing in the data and you keep updating. And the reason it doesn't matter, the reason it doesn't matter if you collect x1 first or x2 or if you do two together or whatever. The reason is that because these measurements are independent, the information that is introduced by, say, the second measurement does not make the information collected in the first measurement obsolete. Once you measure x1 prime, measuring x2 prime does not deny the fact that in the first measurement you got x1 prime, right? That continues to be true. So you do not negate the original information. This interesting conclusion does not hold when the successive pieces of information make the previous ones obsolete. Now that's actually important. When you have independence, then it's fine, but if you don't have independence, then you have to be careful. And in many cases, this is indeed true. So in the future, we're going to have to be careful about this. Very good. I want to talk a little bit more about priors now. One of the things that became clear in this previous example, so let's go back to it. Okay, let me see. In this previous example, we saw that when we perform many experiments, we start with a prior, we incorporate the information from one experiment, and we get a posterior. Then we carry a second experiment, and for that second experiment, then the prior is going to be the previous posterior. So this is more or less general. Today's prior is yesterday's posterior. So that's why it was so important not to waste the valuable information you acquired in the past. The prior information really matters. Okay, you want to keep it because you got it. It comes from somewhere. So this is telling you two or three things here. The one thing that's telling you is that if you perform this sufficiently number of times, maybe it doesn't matter what you pick for a prior, that you have so much information coming from the data that the data sort of overwhelms the prior. Indeed, that intuition is correct. We're going to derive it in a second. Okay, so that's one of the things we want to do. The other thing that we have to do is, well, you start with a prior, then you start updating, and so that the information in the data becomes more and more overwhelming. But what do you pick for the first prior? And there are techniques to pick priors, and typically what you make is an educated guess and proceed. But sometimes you do have good reasons to believe what the prior ought to be. Sometimes there are symmetries. If you toss in a coin, the coin is fair, it's symmetric, you might as well start with uniform distributions, that kind of stuff. So symmetry principles may actually be very valuable. We're going to see that entropy principles can also be valuable in assigning those priors. But one of the things that is clear here is that what you pick for a prior can have influence. In fact, we saw some of those examples just a little while ago. When you're testing for a rare disease, what is the incidence in the population? What is the prior probability of getting the disease? That really matters. So priors matter. So the example that I want to discuss here is be very careful. Caution. What happens if you have strong prejudices? Suppose that on the basis of whatever background information you have, the probability of theta, given any background information that you might have, happens to be 1. Suppose you are convinced that theta is true. Then the probability of, let's just write our Bayes theorem here. You are interested in the probability of theta, given that background information, and we're going to write this as q theta b. And then here you may have data, theta b, and you're going to have some normalization. Now, this is interesting because one of the things that this is telling you is that if given b, you are convinced of theta, then theta b, the truth of theta b is exactly the same as the truth of b. Let me say it slightly different. If assuming b, you know that theta is true, well then assuming b, this can only be true, this is going to be true whenever b is true, right? So this is exactly the same as that. So what this means is that qx theta b is exactly the same as xb, which means that these two guys here cancel out, and p theta b is exactly q theta b, which was 1. Now you see why this might actually be dangerous, because when you are completely convinced in the truth of something, then collecting data to process it uh, becomes completely unnecessary. You're not going to be able to. This theory is telling you that if you are completely convinced of something, collecting data or not makes no difference, and you might be inclined to not collect data at all. You're not going to be convinced of anything by having any data. So uh, if you are completely convinced that Jupiter has no moons, to quote the famous Galileo example, if you are completely convinced that that Jupiter has no moons, then you might not even want to look through the telescope, right? Uh, and if you do look through the telescope, you did collect the data, you might be inclined to actually say, oh yes, I see these shiny spots here, but how do I know that those shiny spots are not due to the fact that these lenses are completely irregular and flawed, so that they might just be artifacts of a bad experiment? Um, Good question. So the conclusion to be drawn for this is that you have to be extremely careful to assign probabilities 1 or equivalently probabilities 0 to something. I mean, same thing works for probability 0. If q theta b is 0, then when you do your posterior, theta b is going to be q theta b, which you see already it's killing everything, q theta theta b x prime theta b. In this case, this is going to be 0, so that's 0, 2. So if you're completely convinced that something is false, it doesn't matter how much evidence to the contrary you might be collecting, it's not going to happen. You're not going to update. So an extremely prejudiced mind is a very, very dangerous thing to possess, because you have no, provided you behave rationally, which is what we do when we do all of this, uh, if you behave rationally, you're never going to learn. So maybe it is a wise thing to do to always keep an epsilon there. You say you're not completely convinced of the certainty of this, call it 1 minus epsilon, because then if you collect enough data, maybe you're going to overcome the bad prior you started with. Same thing here. Instead of putting 0, put an epsilon there, and then you have a chance of actually learning. So this is a cautionary remark, right? The Surgeon General advises you do not assign complete certainty to your beliefs. Of course, should you stop believing that 2 plus 2 equals 4? No, under those circumstances, you're okay. Uh, After all, 2 plus 2 equals 4 ends up following as a deduction, not an inference, from the very definition of what you mean by numbers. But so many truths you can keep, but for the contingent truths of nature and real life, avoid complete certainties. What do we want to do now? Yes, to finish, I want to prove what we have been saying here, mentioned it twice already, which is that if you have enough data, then enough data, if you have sufficient number, you repeat your experiment sufficiently and you have a sufficient amount of data, that may end up overwhelming whatever incomplete information you had in the prior, and therefore it doesn't matter what the prior was. So this is yet another piece of evidence that while the prior may be pretty subjective because you do not know how to really pick it, you just say, well, this feels okay. If you collect enough data, then the posterior will be considerably more objective because the data itself is objective, right? So the objectivity of the data ends up being uh, implemented or contributes to the objectivity of the posterior. In fact, this is why we want to collect data and update. The prior might have been subjective, but posteriors are considerably more objective. The data itself is objective. Very good. So what I want to do is I want to go on to the next little topic, which is interesting. Lots of data overwhelms the prior. So here, this is yet another reason why repeating the experiment over and over and over again is a good idea. Whatever was wimpy, fluffy, subjective in the prior becomes more objective. So what we want to do is consider n independent experiments. N independent experiments. And so the experiments are going to be, I'm going to use the same notation as we had before, x1, xn, and the prior is going to, the likelihood function, x given theta, is going to be a product of the likelihoods for each one of the independent experiments. And we're going to write this as a product of R equals 1 to n of Q XR given theta. Very good. So what we would like to do is say, what is the posterior? The posterior is going to be Q, the probability of theta is going to be the prior, and then there's going to be the likelihood function, QXR given theta, and then we're going to divide by the probability of X. Very good. The way I'm going to think about this is, suppose we want to collect, to perform this inference, and we want to figure out what happens when the acquisition of data leads you to prefer one value of theta over another. That's what we want, right? We want to figure out theta. So you acquire this, presumably this probability distribution will become more and more peaked around, about the correct value. So how does the data force us to prefer one value, say theta 1, over another, theta 2. And to do that, what I'm going to do is I'm going to consider the ratio of two of these guys. And when I compute the ratio, I'm going to have the ratio of the theta 1 of the prior for theta 1 and theta 2. And I'm going to have the ratios of QXR given theta 1 divided by QXR given theta 2. And please notice that the QX has dropped out because there is no theta 1, theta 2. It's the same for both the numerator and the denominator, so that's dropped out. So I'm going to use a notation here that will make this a little bit more reasonable. I'm going to call this Q theta 1, Q theta 2, and this is going to be called the ratio for n, and this is the ratio that depends on the x's, and this ratio is going to be the product of those ratios for each experiment. So I'm going to call this R XR. Very good. So what we would like to show, so this is the theorem. The theorem says that we expect that if theta 1 is the correct value, then as n goes to infinity, then the probability of theta 1 divided by the probability of theta 2 should become very, very large. In fact, if theta 1 is the correct value, the probability of theta 2 should go to 0, right? And so this should go to infinity. So that's what our theorem is supposed to be. Given theorem, let me say, this is a sloppy version of the theorem. We expect, that's what the sloppy version of a theorem is, it's an expectation, that given theta 1, assuming that theta 1 is the correct value, the true value, we have R, that ratio x goes to infinity. Now, this theorem, as stated, is not true, but if I say it goes to infinity in probability, then it is strictly true. The probability that R does not go infinity actually goes to 0. So if we want to be a little bit more rigorous, we're going to say alternatively, the limit as n goes to infinity of the probability that R differs from that R is bigger than a number, conditional on theta 1 being the truth. This is actually 1. So the probability that R is bigger than any number whatsoever, right? This is any arbitrary number. Any, let's even call it any large number, no matter how large, is equal to 1. So how do you prove this? There are exceptions, right? With two exceptions. Here are the exceptions. When we look at the expression for this object here, we see that if the priors here, q theta 1 or q theta 2, happen to be, so for example, if q theta 1 happens to be 0 or 1 or something like that, if you have already certainty, then it doesn't matter what you're doing, you can't update, right? One is when you're extremely prejudiced, and when you have q theta 1 equal to 0. You can't update there. Or q theta 1 equals to 1. You can't update there either. So, and you see the problem of the prejudice mind is actually serious. The second situation is the one in which, well, okay, you're fine, these two priors can be different, they're definitely not 0 or 1 or all that. But if your experiment is such that the likelihood for theta 1 is exactly the same as the likelihood for theta 2, that means that your experiment cannot distinguish, measurements of x cannot distinguish between x1 and x2. So under those circumstances, qxr given theta 1 is equal to qxr given theta 2, that your experiment cannot distinguish theta 1 from theta 2, and this is indication that you have designed your experiment badly. Bad experimental design. Clearly, if you want to measure something, you want to make sure that it makes a difference, right? So except for those two conditions, and we're going to see how they appear in a second, this theorem is true, and that means that collecting more and more data will make the probability of this ratio being large more and more and more likely. So how do we proceed? The proof of the theorem proceeds by using the central limit theorem. Actually, the law of large numbers. Use the law of large numbers. This is actually kind of useful. Let me see. We are going to consider the quantity 1 over n, the log of r. Now, what's r? If you look here, r is a product. The law of large numbers was saying something like, if you have one quantity, which is the sum of many, many, many little quantities, then blah, 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 you have your theorem, right? So in order to apply the law of large numbers to any inference about this quantity here, what we would like to be able to do is replace this object here, which is a product, by a sum. The way to do that is to introduce logs. So this is what we're going to do. And so what we have here is going to be the sum of r equals 1 to n of 1 over n, the log of r x r. Then, since these variables log r x r are independent, we actually have that the limit as n goes to infinity of the probability, and here we're going to write the probability that the quantity 1 over n log r differs from the average. I'm going to write the average as a capital K. Differs from the average by less than a small amount, given theta 1 is equal to 1. So the quantity log r over n is going to be very close. The difference of this quantity from k is going to be less than an epsilon. For any small epsilon, that goes to 1. So that's what it means to say that it converges in probability. What is k? K, theta 1, theta 2 is going to be the average of 1 over n log r of x given theta 1. And what this is the average of qxr given theta 1 log Q, the log of R. Let me write it out. R XR. And here I'm summing over all the XRs. Now, this guy here is a sum. I do one sum. That's what I wrote here. It comes divided by 1 over n. But I have n of these terms, and they all give the same result, right? So the 1 over n cancels out. So you have 1 over n, and then you have n terms like that. So this is what the k is. And so what this means, therefore, is that assuming theta 1, there you go, assuming when theta 1 is the true value, then the quantity R is going to be contained between, well, if this quantity is going to be very close to k, then if 1 over n log R is close to k, then this quantity here is going to be contained between nk plus some epsilon, and then here I'm going to have nk minus some epsilon. So this proves it. As n goes to infinity, the probability of R, put it again, in probability, the quantity R becomes bigger and bigger and bigger. Or the probability that R is as large as you want becomes larger and larger and larger. So that proves it. So what this means, let's go back to this. How is theta 1 favored over any other theta 2? Well, you collect your data. Of course, if you collect data, the data can be anything you want. And so this quantity here can take any value you want. However, the probability of this quantity is that it's going to be very, very large. So that means that theta 1, the true value, is preferred. The quantity that we have here for k is actually kind of interesting. And I'll finish here. The quantity k is interesting. Let's write it out. Let's go back here, remind ourselves what it was. We wrote it here. It's this expected value, which is 1 multiplying for any xr. You just do this calculation. And what's r? Go back yet another one. And we have that the RR is one of these factors. It's the likelihood ratio. It's a ratio of the likelihoods. So the quantity we have here for any XR is the probability of XR given theta 1 multiplied by the log of the probability of XR given theta 1 divided by QXR given theta 2. This quantity here is going to be central to whatever follows in this class. This is the very first appearance of a quantity that's normally called relative entropy. Minus k actually is relative entropy. It goes by other names. Sometimes it's called the Kullback-Leibler distance. Terrible name because this is not a distance. It's not symmetric in theta 1 and theta 2. Sometimes it's also called directed divergence. Sometimes it's called relative information. So all sorts of bad names. Relative entropy is probably the better name of them all. There is one aspect of this that I forgot to address, which is when I write an inequality like this, and you say that this is true in probability and all of that, this will mean that R goes to infinity, provided this K here is positive. So we're going to prove this later. It's called the Gibbs inequality. He was the first person to write an inequality like this. This quantity here is bigger or equal to 0. It is equal to 0 if and only if, how do you get a 0 here? Well, the log of 1 is 0. So what am I doing here? QXR given theta 1 is equal to QXR equal to given theta 2. So what we see here is that indeed, if your experiment is badly designed in such a way that the measurements of x's do not make no distinction between theta 1 and theta 2, indeed, your data, multiple experiments with data is never going to overwhelm the prior because the experiments are not carrying any kind of information. That's the second type of exception to the rule of lots of data overwhelms the prior. The first one, of course, was the fact that there is a prior here. So if you put 0 there, it doesn't matter what you do, you're always going to get 0. Very good. With these ideas, we are more or less done with the foundations of probability theory and of Bayesian inference. There is more stuff in the book, in the lecture notes. There is the section on hypothesis testing and confirmation, which is crucial for scientific inference. You have a hypothesis, you want to test it. You want to corroborate the hypothesis or refute it. And there is another section on just plain data analysis. I'm going to skip those two sections for two reasons. One is that there is another course in this department that deals purely with data analysis, Bayesian inference and data analysis. So that material is covered elsewhere. And second, I want to really focus more on physics as opposed to data analysis. So by not covering the data analysis part, I'll have more time to talk about physics. So next class, we start talking about the application of, we start talking about the appearance of entropy in physics, how it started. So we start with a little bit of thermodynamics next class. See you then.